In this video, we will talk about efficiency of recursion. So recursion is a powerful problem-solving technique that often produces very clean solutions to even the most complex problems. Recursive solutions can be easier to understand and to describe than iterative solutions. By using recursions, you can often write simple, short implementations of a solution. So many of the recursive solutions are inefficient that you should not use them. So for our example here, the Fibonacci sequence, if we want to find the nth Fibonacci number in the sequence, if we use this recursive function, this is a very inefficient recursive solution to this problem. So two factors contribute to the inefficiency of some recursive solutions. The first factor is the overhead associated with function calls. And the second factor is the inherent inefficiency of some recursive algorithms. So the first factor, which is the overhead associated with function calls, does not pertain specifically to recursive functions, but is true of functions in general. So in most implementations of Java and other higher language programming languages, a function call incurs a certain amount of bookkeeping overhead. As was mentioned earlier, each function call produces an active record, that's to say the stack frame on the call stack. So the recursive functions magnify this overhead because a single initial calls to the function can generate a large number of recursive calls. So for example, the call factorial of n actually generates n recursive calls. However, if you just use a for loop to find the factorial of n, you just create one frame, one stack frame on the call stack. However, if you use factorial of n, if you use recursion, then you have to have n stack frames on the call stack. So that will incur more bookkeeping overhead. Okay, so in that way, actually, we don't want to use a recursive solution if it's inefficient and if you have a clear, efficient, iterative solution. So for some of our problems, for example, the tau colloid example, actually, that's a very good example for the recursive solution because we can get an elegant, concise, clean, recursive solution. However, for the iterative solution, it's hard to construct. So for some of the problems, actually, we could have a very efficient and clean, concise recursive solution. But for this Fibonacci sequence number, the factorial number, the factorial of a non-negative number problem, they are not as efficient as some of the other problems if we use recursion to solve them. Okay, so the second point about recursion and efficiency is that some recursive algorithms are inherently inefficient, just like what we talked about, the Fibonacci sequence problem. If we use this Fibonacci, if we want to use recursion to solve this problem, actually it's very inefficient. And if we want to use recursion to solve the factorial of a non-negative number, it's also a very inefficient algorithm. So this inefficiency is a very different issue than that of overhead. It has nothing to do with how a compiler happens to implement a recursive function, but rather is related to the technique that the algorithm employs. So for example, if we look at our Fibonacci problem, so I just use acronym FIB to represent this Fibonacci because I don't have enough space on my slides. So we use this fib to represent this Fibonacci recursive call. Okay, so for this Fibonacci sequence problem, the figure on the right-hand side of the slide illustrated computation of Fibonacci 7 here. So the fundamental problem with Fibonacci is that it computes the same values over and over again. And you can see here, I didn't list all the recursive call because I don't have enough space on the slides again. So as we could see here, even though we didn't have the complete recursion tree on these slides, we could see here FIP5 has already appeared twice, and not mentioned the FIP2, FIP3. So FIP2 actually repeated several times, and FIP3, FIP4 repeated several times. They just those values just computed over and over again. So when n is relatively large or moderately large, many of the values are recomputed literally trillions of times, and this enormous number of computations makes the solution infeasible, even if each computation requires only a trivial amount of work. So if we could come up with a very concise, clear, efficient, iterative solution for those kinds of questions, like the Fibonacci problem and the factorial problem, then we would not choose the inefficient recursive solution. So now let's talk about the Stack Overflow with some of the large input. So whenever we call a function, including recursively, the return address and often the arguments are pushed onto the call stack. However, just like the call stack we have here, so if we look at our factorial problem here, we want to get the factorial of non-negative number n. We say that we have the base case when n is equal to 0, the factorial of n, 0 is equal to 1. That's our base case. And we also have this recurrence relation. We say that factorial of n is equal to n times factorial of n minus 1. So this is our implementation of this factorial of n. So think about if n is very large. So for example, if I have a main function and I call this factorial of 4 billion, I want to get the factorial of 4 billion, how I can get it. So if I use this recursive solution, then when I have an initial or the original call for this factorial of 4 billion, actually I will have 4 billion stack frames on this call stack. However, so we are going on and on until we get to n is equal to 0. When we reach the base case, we will stop and give back the value, return the control back to our main. However, our call stack is finite. So if the recursion is too deep, you will eventually run out of stack space. You will eventually run out of memory space. And our call stack is where function calls are stored. You can see here, we stored our function call, the main function call, the factorial, when n is equal to 4 billion, and so on and so forth. So when a function is called, the control needs to go into the function. When the function completes executing, the control needs to go back to the function it was called from, and the call stack keeps track of the current executing function, and the function it needs to go back to when it finishes executing. The number of frames the stack can hold is finite, just like you said, you see here. So if we have we have a very large n as an input, like 4 billion, which is the value for n, then we should have a 4 billion stack frames on our call stack. That will help us, that will lead us to run out of stack space. When the stack can take no more frames, it's said to be overflow. That's you get the infamous stack overflow exception. So it's important to learn to break things in order to prevent it from breaking. So we want to avoid using recursion to solve this kind of problems when we have a more concise and efficient iterative solution.